semester. I'd like to introduce Professor Areg Danagoulian. Areg is an assistant professor at the Nuclear Science and Engineering Department at MIT. He's actually an NC State alumnus. He got his undergrad in physics just across the street in Riddick, and does PhD in experimental nuclear physics at the University of Illinois at Urbana-Champaign. Following the graduation, by the way, his PhD work was on probing the internal structure of the proton, but after he finished, he went to work at Los Alamos for a while and worked for a company called Power Systems Incorporated in Boston. They focus mainly on purposes. And then he later joined the MIT nuclear engineering faculty. His research interests are primarily in nuclear nonproliferation and nuclear security. And so today he's going to tell you about some of his work, particularly on using resonant phenomena for nuclear disarmament verification.
All right. All right. Thank you, John, for the great introduction. Everyone can hear me, more or less, yeah? Okay. So, by the way, it's great to be back to NC State. Like, I was here about 2 years ago in Raleigh, but I didn't have time to visit the campus. But effectively, I haven't been here in 23 years. The place has both changed and not changed at all at the same time. All right, so nuclear disarmament, resonant phenomena, what I'm going to talk about, just to give a quick outline, because I'm going to cover a lot in the next 50 minutes or 45 minutes or so. So first I'll talk about what is this big problem that we're talking about. Okay, what is arms control, what is nuclear disarmament, and then we'll talk a little bit about history of treaty verification. Okay, how have people approached this problem in the past? And I'll talk specifically about a general paradigm within which we try to operate called template verification. There's different approaches. It's a kind of like an approach. It's not technology yet. And then specifically within that approach, I'll talk about what technologies we can use, okay, to achieve the goal of the verification without revealing any sensitive information, which is extremely important criteria. And finally, I'll talk about epithermal neutron physics. As well, I'll talk about nuclear resonant fluorescence very, very briefly. So we'll start off from very general policy towards technology and like technological solutions. Okay, so quickly, like where do things stand currently as far as nuclear weapon arsenals are concerned, and where were they in the past? So currently there is about something like 15,000 warheads throughout the world. This is the sum of all the warheads, and this is the US stockpile, Russian stockpile, and this is everything else. Okay, and things are, 15,000 warheads is quite a bit, but it used to be even worse to the height of the Cold War. So 1985, I believe the number went up to like 70,000. Okay, and for people who maybe don't know exactly what is the power of a nuclear weapon, just like think about the bombs that were dropped on Hiroshima and Nagasaki, killed about 100,000 people, and modern weapons are a lot more powerful than that. A significant part of the arsenal are thermonuclear warheads that are about 20 to 30 times more powerful than what was used on Japan in 1945. Okay, so how did this drop happen? This is great. Well, there was a treaty that was signed called Intermediate Nuclear Forces Treaty, which stipulated a dismantlement of whole class of delivery systems and their warheads, okay, which really allowed now to get the numbers to come down. A number of additional treaties were signed, START Treaty, the SWORD Treaty, and then finally the New START Treaty, which stipulate further reductions. Okay, so. All right, so these are the number of the warheads currently in different arsenals for different countries, and you see that basically 90% of the warhead, 90% of nuclear weapons are in the hands of the Americans and the Russians. But the other one thing I want you to look at is that this hashed area, which is the number of the deployed warheads. Okay, so there's a difference between deployed warheads and stockpiled or kind of retired warheads, which are these ones over here. Deployed warheads, the word deployed means it's ready to be used. Okay, it means a warhead that is, or a bomb that is on top of an intercontinental ballistic missile, or on top of a submarine launched ballistic missile, or ready to be loaded into a bomber and sent for a strike, for a nuclear strike, and things like that. And then there's all this basically excess of nuclear weapons that we have, okay, that their numbers are really not coming down very much. Okay, some of them are being dismantled slowly, but significant parts, both the United States and Russia are trying to hold on to. Okay, so while there was a significant reduction from Cold War era, there's still this we have this stagnation of this large, still fairly large stockpile. And we hope that there will be some treaty signed in the future that will really go after these things, after these extra warheads. Now, the question that you ought to ask yourself, like, okay, we have really brought down these numbers, but these treaties are great, but they're meaningful only if you can verify them. So, Ronald Reagan liked to impress Mikhail Gorbachev by learning little quaint Russian phrases. And one of them was, доверяй, но проверяй, which means trust but verify, right? So question, like, how do you do that verifying part, right? That's fairly difficult. And before getting to that thing, just to kind of talk about the current state of the affairs, okay, is, there's lots of bad news that we're hearing from Washington. One of them is we're pulling out from the intermediate ballistic, intermediate nuclear forces treaty, the one that caused that rapid decline that I showed you earlier, for a whole variety of reasons. But at the same time, if you read the nuclear posture review from last year, it says that, it fairly stipulates very clearly that US will continue its efforts to seek arms control agreements that enhance security and are verifiable and enforceable. So having verifiable treaties is extremely important, okay, in order for them to be worthy. Okay, so how did we verify things in the past? How did we verify the dismantlement of nuclear weapons in the past? The short answer is we never did. Okay, what we verified instead was the dismantle of the delivery vehicles. Okay, so what's a delivery vehicle? It's whatever delivers the weapon to its final destination, to the target. So examples of delivery systems would be bomber aircrafts. It would be intercontinental ballistic missiles. It would be cruise missiles. It would be submarine launch ballistic missiles, etc., artillery, if you want. Okay. So in the 80s, we signed the INF Treaty, and the way people verified that is the two sides brought out their emptied out cruise missiles, which are primarily targeted cruise missiles, and the other side came and eyeballed the cruise missiles and said, yep, this looks like a real cruise missile, it's not made out of plastic or plaster or something like that. Cart them off towards mechanical dismantlement or destruction. So this is Griffon, American cruise missile, is like nuclear equivalent of a Tomahawk. This is an example of fairly old intercontinental ballistic missile that, this is the Senator Lugar that signed the Lugar non-threat reduction treaties. Agreement, threat reduction agreement. So again, he looks at an ICBM, yup, it's a real ICBM, destroy it. And then the most interestingly, when the Americans and the Russians at this point signed the START Treaty in 1994, I believe, as part of that, Americans agreed to destroy 365 of their B-52 bombers. Okay, and the way they did that, they took them out to the Arizona desert. They brought these large guillotines, they chopped these airplanes in pieces and let them sit and dry in the desert. And then the Russian satellites flew overhead, took pictures. Russians look at the pictures and says, yep, okay, they truly did destroy their, and if it's kind of, could you fake something like this? Maybe you could, but it's very difficult to do it without getting caught. So this is something that you could do with large systems, okay? The trouble is that, if you look into the actual, what the nuclear warhead, after the nuclear warheads, because end up having these very large stockpiles, the trouble with them is that while, bombers and ICBM are these large systems, the nuclear warheads, this does not work, and now it works, okay, is that this is what warheads look like, okay? These are black cones about this big, about human height size. Okay, this is a re-entry bus of the Peacekeeper missile, which now has been retired. It can carry up to 13 independently targetable re-entry vehicles that can strike 13 different targets. Each one of them is about half megaton, which is about 25 times more powerful than the Hiroshima bomb. Each one of them. Their combined explosive power is more than all the explosives detonated during World War II, okay, in terms of a comparison. And of course, there used to be hundreds, if not thousands of these missiles during Cold War. So the difficulty here is that how do you verify that this is a real nuclear warhead without looking inside? Because if you look inside, you find out sensitive information, and nobody will ever agree to sign any kind of a treaty where you explicitly can look inside the nuclear warhead. That would just not happen. So the paradox is that we need to find a way to verify the authenticity of these things, of these weapons, without looking inside. And that seems to be like a paradox. How to prove that this is a warhead without looking inside? So this is, there have been significant number of attempts in the past, but in order to sort of kind of tell you what people have tried, one system that people have tried was called information barriers. People worked on, attribute verification systems, where effectively the idea was that you're going to have a warhead, we're going to do a measurement, which the data itself will be very, will contain lots of sensitive information, but information barrier, which is basically the electronic computational cryptographic system that will compare the measurements from the warhead against some very general parameters. Those parameters have to be very general, otherwise you'll learn stuff. And then if they match, then thumbs up, okay, and green lights. If not, red lights, okay. So for example, there will be questions like, is there more than half a kilogram of plutonium inside the bomb? Yes, green lights. Is there explosives inside the weapon? Yes, green lights, or something like that. And again, this has to be extremely general. It cannot be, is there between a kilogram and 1.1 kilograms of plutonium? Because if the green light comes up, now you have found out a lot about the warhead. So just to tell you that the problem with this approach, which sounds very attractive, if you think about it from the beginning, is following analogy. Imagine you have got a black box with a rabbit inside, and you're trying to prove that this is a rabbit, but you don't want to find out any classified information about a rabbit. Okay. So first thing you can do is you can insert some probe and take a piece of the DNA. Is it, maybe I have to be closer for this to work? Oh, there you go. You have to take a piece of DNA and you can verify that, yeah, this is a real rabbit. Problem, you'll find out the length of its ears, the color of its fur, if that might be clever, or its explosive rabbit from Monty Python. Instead, what you do, you put some kind of like a barrier, like an electronic computational barrier that takes a piece of DNA, does some comparisons, and answers. Okay. It says, does it have long ears? Yes. Does it have big feet? Yes. Does it have a fluffy tail? Yes. So, it must be a rabbit, right? Right? Well, this is a picture of my dog, okay? He has long ears, and he has a beautiful fluffy tail. So the problem is that by insisting on such general criteria, effectively, okay, and these criteria have to be general, otherwise you find out too much. By insisting on such general wide criteria, you are allowing all these kind of hoaxing scenarios that can happen, okay? But there's an additional problem. It's not only hoaxing. The problem is that you are relying on electronics and on software to do this verification, okay? This creates a problem. You can leak information, can provide false results. Basically, what happens is that if you rely on information barriers and computational cryptography, you are shifting the burden of the verification from the weapons to the information barrier. And now you have to verify the information barrier. And that's very hard to do, because an electronic system has millions of components that are extremely difficult to verify. So in terms of like the things, how do you do a verification that is both secure, okay, and accurate? Okay. So we could use, software encryption, something that does like analysis and then just says yes or no, all clear or false or something like that. There's problems with that because now you have to verify the code. You could rely on electronics, okay, to do this. There was this interesting article in Bloomberg about tiny pieces of electronics embedded in hardware. It was quite controversial, but it sort of gives you an idea of what could happen. Now you have to verify electronics, and that's very hard. So I would argue that the best way to do this kind of a problem is through physics itself. Process where the encryption is done through the intrinsic physics of the measurement, rather than through electronics and software. The reason is because electronics and software are mutable. They can be changed, okay? They can be hacked. Laws of physics cannot. Okay, you can learn them, you can understand them, and now you don't have to trust the other side. You have to trust your own understanding of physics to some degree. There's like, okay, so how do we do it? Okay, how do we use physics to improve stuff? Okay, so in general, again, I'm staying very high level. I have not talked at all about the technology or the technological concept or even physics with which we're going to do it, but just in general to understand the underlying approach that we're doing is the following. And an alternative way of approach, rather than doing this attribute verification, you can do something that's called template verification. Under template verification, what you do is you get a hold of something called a golden copy. You get one unit of a particular weapon design that you know is authentic. Okay, that one is authentic. How do you do it? You could, for example, do random unannounced visit to an ICBM site and pick a random warhead off of a random ICBM. In order for the country to have a nuclear deterrence, it needs to have real weapons on their ICBM. So if you got a warhead from an ICBM that is on duty on a country that clearly needs nuclear deterrence, you know that at least that unit is a real one. It's not, that one cannot be fake. Otherwise they would lose they would be risking their deterrence, and they would not do that. Now what you are doing, now you are comparing this golden copy to candidate copies of the particular design, okay? And you ask, is the golden copy identical to A1? Is the identical copy identical to A2? And if they are identical, whatever that means, we'll have to define it in the next couple of slides, then say, well, if this is real and they are identical, then this one is also real, authentic, and this one is authentic, this one is authentic. Send them off to dismantlement and count warhead dismantlement towards that country's obligation under the treaty. All right, but how do you do this? What this equal sign, what does it mean? Okay, and in order to do this equal sign correctly, you need to achieve two things. One thing is that you need to protect secrets. Okay, you cannot disassemble these warheads and compare them like screw by screw, right? It's out of fashion. And second thing is that whatever it is you are doing, okay, has to be isotopically sensitive. Okay. Simple X-rays are not going to work because multiple materials will produce the same X-ray image. Okay, they could build something that is on an X-ray looks identical, but in reality is very different. You want to have a one-to-one map between measurement space and isotopic geometry space. Okay, and simple X-ray is not going to do it. You also, so the best way of doing that is, well, I'll tell it in the next couple of slides. Let's see, a bit closer. Okay, so so you could do this naive verification where you just compare A1 to 0. As we said, you are going to learn lots of sensitive information about A1, A0. But something that you can, then doing a comparison, okay, you can convolve the signal from these two things with some kind of a key. Okay, you can have some secondary process, okay, whose signal is mixed with the signal from your main weapon, and now you are comparing the convolved processes. Okay, one way to think about this is that you are using the same key to do some kind of a hashing of the original signal, except like the word hashing, we think of computation. Here it has to be done through physics, okay, not through computation. And if you can pull this off, now you're comparing signals which, if they are identical, and if the key is identical, it means the underlying object is also identical. And if you have done this hashing or this convolution correctly, from a signal you will never be able to uniquely infer anything about this object itself, because you have kept the key secret. Okay? We'll talk a bit more about what this actually means. One way to think about this is checksums, right? We use checksums. You download an image of an operating system, and what if someone injected a modified version of operating system? So what happens at the website, typically is canonical if you're downloading an image of Ubuntu, of a hash for an MD5 sum, right? And you run MD5 sum on that file, okay? And if the hashes match, it means that the files were also identical. And yet from the hash, you can never infer the content of the file, okay? So same key, you're comparing two files, same hash means same files, and yet from the hash you cannot infer anything about the file. Okay. Okay, but again, is not good enough. Let's see. Oh, okay. All right. So just a quick just description about the history. Okay, is people have worked on these different concepts for quite some time. Okay, people have worked on template verifications, is what I'm talking about. People have worked on attribute verification. Nation labs have done quite a bit of this work, as well as thinking of this template versus attribute and things like that. So there's like two. Okay, or passive. So basically what we want to do physical cryptography. And essentially what we are working on is in the domain of physical cryptography using template verification. There's another concept developed by Princeton. Okay, they use fast neutrons for radiography. And people at the Sandia and Berkeley in Michigan are working on coded. I mentioned earlier that it has to be isotopically sensitive. It has to be a one-to-one map from isotopics and isotopic geometry to your measurement space. Okay, X-ray doesn't do it. Okay, so it has to be nuclear structure. Okay. So this is where there's a real benefit in using resonant phenomena. Okay. Resonances effectively give you a unique signal to particular nuclear, bound state. Okay. So the idea is that you have got, for example, this is the nuclear levels for uranium-235. If you hit it with the right photon, or it doesn't have to be photon, it can also be electron or something else, you excite grounds the nucleus to an excited state, then you have a decay, and end up having photons of a particular energy. So you can do this with photons. This is what's called nuclear resonant fluorescence. And however, you can also do it with neutrons. Neutrons also can trigger resonance. Scale is lower. This is at MeV. This is about EV. And just kind of for people who are maybe not familiar with nuclear physics, is think about atomic fluorescence. Right? We have, atomic emission spectrum for hydrogen, for sodium, and essentially you kick up the atom to its excited, they decay back down. Nucleus is just state. Okay, you have the atom, whether it's nucleus or whether it's a hadron, protons. If you kick them hard enough, you'll get this sigma resonances and things like that with emissions of very specific energies. Okay, same thing over here, and you can do this two ways. One of them, you can either have an emission spectrum or you can have an absorption spectrum. Okay, where you shine, essentially continuous to your material, and you end up having absorption at energies that are specific to that atom or nucleus, depending which one you are doing. Okay, so I'll talk very quickly about NRF, just really, really briefly, because we're very short on time, and then I'll talk mostly about neutrons during this talk. In case of NRF, a Bremsstrahlung beam. Okay, Bremsstrahlung beam, you get electrons on a piece of metal. That gives you that continuum. You have we did this experiment where we put together this proxy warhead. We don't have warheads or laying ground at MIT, so we use something that has some of the warhead. That really matter. So we had depleted uranium, some aluminum here, and some plastic. Depleted uranium is a proxy for HEU, and plastic is a for explosives, and we also had some aluminum. So this is secondary encrypting foil. Okay, so what we measured was not the NRF from the weapon itself. If we're thinking about the weapon, we learned it from a secondary object that is provided by the warhead. The host builds that key filter or encrypting foil. Okay, and then you measure a signal from this device over here. Okay, this ends up being an underdefined. Your signal depends on this and depends on this, and you know neither equation. Okay. But the important is that one of those unknowns is kept constant, so you can switch between two objects, and as long as the second unknown is kept constant, now you can, as long as you get the same signal in both cases, you can verify that the first part was the same as well. Okay. I'll talk a bit more about that, so to make it more clear. Okay, so we did these measurements, nuclear resonant fluorescence. These are the different resonances from aluminum and uranium, because big resonance is aluminum. These ones are uranium-238 lines. And then what we did was we changed the uranium with of an equivalent attenuating thickness. Not same thickness, but the thickness same, not attenuation. Continuum would be the same. And when we did that measurement, we got a very different signal. Okay, so we're trying to ask, is this technique sensitive enough to be able to see a difference when you change the isotopics of the object? Okay, and we essentially got something like 11 sigma difference. Just for reference, 3 sigma corresponds to like 1 part per 300, so 1,000, something like that. Probability, it's just a random fluctuation. 11 sigma is a complete rule out, so zero probability. So you can tell very clearly that this difference is due to systematic effects, which is a cheating attempt, essentially. Okay. So we published this work earlier to go and read and learn more about this. And now, while photons are great, there's a number of downsides to photons. Photons are great because they are very penetrating. The downsides, there's a series of downsides. One of them is that you need a very complex hardware. You need germanium detectors. You need CW accelerators, which are big, complex, and expensive. And there may be a better ways of doing this using neutrons. Okay. So just like photons, neutrons too can induce resonances or resonant behavior in nuclei of importance. These are the cross sections for plutonium isotopes, showing very clear resonances at electron volt scale. Okay, so electron volt neutrons are, we call them epithermal neutrons. I'll be referring. Every time I say epithermal, it means something between 1 and 200 eV. In reality, epithermal regime is much broader, but these are the ones that we care about. The important is that you end up having this clear and still distinct resonances. When you go to higher energies, resonances become much more compact, becomes very hard to measure them individually. Okay. So the notion is that you have got some kind of object. If you shoot a beam through this of epithermal neutrons, and if you have a detector which can measure both the energy, say through time of flight measurement, and can measure the coordinate, okay, then for every pixel you can get this absorption spectrum. Remember that absorption spectrum I showed for sodium and hydrogen? Same thing here, a continuum with bunch of energies missing that correspond to that particular element. So by looking at the position of this missing peaks, these absorption lines or notches, you can infer which element is present. By looking at the depth of these lines, you can infer its amount. Okay? If you do it for every single pixel, you can do isotope-specific imaging of the material. Okay, it's a fairly powerful technique that has been developed in the past. Who are using it for this work. So some examples of what people have done: they have taken, samples of depleted uranium with, and then put your energy window on neodymium's resonances. You can see the neodymium, imperfections, the impurities directly. If you put your window on uranium resonances, you can see just the uranium, and you can sort of see that these things belong over here. In a more interesting kind of example, that was used for doing archaeology, actually, like real history archaeology. Here's an example where people put a bunch of wires of tin, indium, and copper, and this is what you get if you just do regular thermal transmission imaging. But if you pick their energies correctly, you can image specifically, indium, tin, and copper. Okay, so it can be a very powerful tool. Now, the question is, how do we use it for weapons? If I were to do this on a weapon, I would learn everything about it. So there's an additional thing I need to do to zero knowledge it out, to do physical cryptography. Okay, how do we do that? So what we do is we do a measurement of an object with a key. I talked that you have some key, some object that adds to the physical process in a way so that you cannot make a unique inferences about the important object itself. Okay, so in this case, this object, like the pit is the sphere that is at the center of a nuclear weapon. This is, so the host provides the pit. The host also provides this cryptographic reciprocal or cryptographic filter, just think about it, okay? Such that in this specific example, where the thickness of the reciprocal is changing such that the sum of this plus this is constant throughout this plane. Where the pit is the thinnest, the reciprocal is the thickest. Where the pit is the thickest, the reciprocal is the thinnest. So that they add up to a constant density. If you get a constant error density, you ought to get a flat image or something image. And flat image plus some Poisson noise, gives you nothing. Okay, there's like no structural or isotopic information in that. Okay. Okay. So first thing that you do, okay, we want to find out, okay, same thing like before. This idea of work is density good enough? I mean, just because there's resonance does not mean that they are going to be statistically significant for you to be able to do measurement. So first thing that we did was I said, okay, imaging-wise, can we see a difference in a scenario where you have, I'm sorry, let me just step back and say exactly what is the approach, just to describe what it is, what this physical encryption is about. Notice is that first you do some kind of a measurement, okay, and that gives you some kind of a spectrum, okay, with absorption lines at the specific energies. Okay, that corresponds to whatever is inside the material, and you can also get an image, right? So you do it with your golden copy, that gives you. And now what you do is you replace your genuine object with a candidate object, an object that whose authenticity you are actually verifying. Okay, and you do a second measurement where you keep this cryptographic reciprocal in place. Okay, and now you do a measurement, and hopefully you get a flat image, and hopefully you get an identical spectrum. Okay? And you ask yourself, are these two signals identical to each other? Is blue are blue and red are identical or not. And if they are identical, it means that underlying objects are identical too, because this is your total signal, which is essentially a product of your object or convolution of your object and the reciprocal. Okay. If the reciprocal was kept in place, it's the same too. Again, it's an equation with two unknowns. You cannot infer anything about the object because you don't know reciprocal. This is like A plus B equals something. If you don't know what B is, you cannot find out what A is. At the same time, if you keep B constant and you see you are getting the same product at the end, it means A was also the same. All right? Okay, will this thing work or not? So first thing that we did was that we essentially run simulations. Again, we don't have plutonium pits at MIT, but you can simulate this, you know. There's lots of things you can do using simulations. Okay, so we essentially took a geometry from open source literature of what a pit looks like, from the Black Sea experiment that John knows a lot about, but tell me. And we constructed an equivalent reciprocal, and this is the image that you end up getting. Okay, this is where in coordinate space, not in energy space. Then what we did was we replaced this weapons-grade plutonium pit with a reactor-grade plutonium pit, which is essentially same element except different isotopics. And I'm having lower amount of plutonium-239, higher amount of plutonium-240, but it has been kept in for too long. And this is the image that you end up getting. Okay, so for the hoax. So just from the images, you can tell clearly that there's a difference, right? But there's something else too. Tell the actual geometry of the pit. Okay, which in a good way, it means that one, their code. Second, their classified information comes out. And if you read the definition of the zero knowledge proof, which is sort of what we're trying to base this on, it says that information will be secure for an honest prover. If the proof is not honest, all the bets are off. Okay, so this is consistent with the requirements of a zero knowledge proof. Similarly, we can look at the energy in the energy domain. Okay, so the blue is a weapons-grade plutonium spectrum. Okay, these are the These notches that you see are results of plutonium-242, 241, 239 has a huge resonance that essentially blacks this out, and 241. This is you end up getting these notches over here. If you change this to reactor-grade plutonium, the spectrum becomes completely different. What happens is that you end up you increase the abundance of all these elements, which completely change the spectrum. These notches become quite a bit deeper. Okay. And that changes the shape of the spectrum. Now you can, do simple chi-square tests and ask yourself, are they the same or not? Clearly, they're not the same. Something to think about here is, to consider here, is like when we do like gamma spectroscopy or something like that, we typically just use the peaks themselves, right? And then we try to subtract the background. Here, we're using the whole spectrum. We're not just using the peaks. We're using everything in between as well. Okay, like this is kind of like coded apertures in energy domain, sort of. You can also ask, okay, how many neutrons do I need to be able to have, say, a 5 sigma detection? Okay, it can be also 10 sigma, whatever you want. And if you take this example and you just do the calculation, you find out that you need something like 100,000 to 1,000,000 neutrons to be able to do this. Most neutron sources will deliver that to you in minutes, if not seconds. It's quite easy to, there's so many ways of making neutrons. That's the nice thing about them. The reactors, spallation source, isotopic sources, LINAC, many different ways. Okay. The thing that you are going to get a flat image, and flat image is going to have no information in it. Well, you should have told me, wait a minute, you lied to us. It's not flat. It's non-flat. What if this non-flatness has some information embedded in it, and someone will throw their deep learning algorithms and learn something about the geometry and whatnot? So, okay, we tried to understand what's going on and found out primarily because of in-scatter, which has nothing to do with geometry. It primarily has to do with distances, with material, and things like that. So we said, okay, what if we replace this pit reciprocal complex combination, which has geometry that we're trying to protect, with just a flat plate of the same equivalent areal density? What signal will we get? And this, we end up getting the same distribution. And this is the radial distribution of the counts, okay, with the error bars corresponding to what you would get under a 5 sigma measurement, okay. And you find out that even if there is difference, it's much smaller than the statistical significance. The difference is much smaller than the statistical fluctuation that you would end up getting, okay. So effectively, if you statistically are unable to distinguish between this and that there's no geometry you're going to learn from this. Okay. You can same essentially tests for, sorry, cannot really see this. You can find out that you can also do this in isotopic domain. Okay, what if they take a spectrum from there and infer the average isotopic ratios of the pit plus reciprocal? They will do that. However, they will be able to uniquely identify which one the reciprocal or the object, what isotopics they have. They don't have to be the same. Isotopics don't have to be the same to pit and reciprocal. Okay, they will learn the average one. But again, you learn the average from 2A plus B, okay? And you cannot infer A separately. To prove this, what we did was that we took multiple combinations with opposite isotopics. This one is more in the reach, this one less in the reach. This one more in the reach, this one less in the reach. And we did a simulation and again, found out that they're statistically essentially identical with each other. You're not gonna learn anything unique about the pit from this spectral analysis. We published this last year. You are welcome to go and to read and learn more about this. So once we're done with this, these simulations are great, but you want to ask yourself, okay, typical simulations, like the same thing with ultimately you want to go and do like experimental proof of concept, okay, proof of concept demonstration. You want to show that something that works in simulations might not work in the lab. For example, because the beam is unstable, or your detector gain is drifting, or something, or backgrounds, okay, that will kill your signal, okay. So you really want to go to the lab and honestly do a measurement. Simulations are a great way to start and to kind of inform you of what is possible, what is impossible. But that's a necessary but insufficient condition for knowing that this will work. You have to go and do the experiment. So we decided to do experiments. But in the process, we bashed our heads and we thought, of doing this, okay. Do we really have to do this imaging? We talked to the people in national labs and we found out that they're extremely hesitant about any kind of imaging, even with a reciprocal and stuff like that. And when we talked to them, they sort of said, well, you know, we cannot tell you what it is. And well, we said, okay, what could it be? Because it's probably some classified reason why we cannot tell you. And we said, oh, well, machining tolerances. Or topics could be different in the two objects, right? So you have two honest objects, but you know what? One of them has been sitting on the shelf longer than the other one, so its isotopics have shifted a little bit. And now you have built the golden copy, but will not match this, and then you start seeing circles, and that's the end of the world for some people. So okay, well, can we abandon imaging? Do we have to do imaging? Can we just do maybe single pixel measurements where we just have one detector? And well, simpler. We don't have to build imagers and whatnot. But the moment you go from a two-dimensional imager to zero-dimensional, and you need that too. But you can regain the geometric information back by doing measurements under rotations. You can rotate things, and that will activity. Think of it like this: you go to a doctor's office. CT scan is basically a single pixel that just goes around you. And under single measurement, they cannot infer anything about the geometry of your body. But if you do multiple measurements under different angles, you can rebuild your three-dimensional composition. In this case, we don't need three-dimensional images. We simply need to show that the two objects are identical under some geometric limits or something like that. Okay. So it turns out that there is a theory that has been developed which shows that you need to do only a couple of random measurements. 3 or 4 random measurements will essentially rule out any significant geometric differences. Okay. So how we're going to do this? So we're going to use single pixel cameras, and we're going to do effectively tomography, or the crude version of tomography. The notion being is that we'll have a neutron beam. Okay, we'll have some kind of a detector, single pixel. We'll have our object, which for the experiment, again, we don't have plutonium. Sorry about that, but we can use molybdenum tungsten. A molybdenum where plutonium and uranium have. So if we can do this with molybdenum tungsten, we ought to be able to do it with molybdenum or with uranium or plutonium. But the other nice thing is now to build this complicated reciprocal. I can just simply use additional encrypting foil of some unknown amount, which is simply just two-dimensional plate. It does not have to have this complex dimensionality. This is another advantage of doing single pixel measurements as opposed to building imagers. So we did these experiments where effectively we had an object which was 90% molybdenum, 10% tungsten. The notion is like molybdenum is kind of like plutonium-239, and tungsten is kind of like plutonium-240. So like its element to isotope map, and use the lithium glass detectors. And now, just a couple of words, how do we get these neutron beams? Okay. There's many ways of getting electron beams, the neutron beams. We did experiment at the Rensselaer Polytechnic Institute, which is a very nice neutron beam line. The way they get their beam line is they have an electron, so one way of doing this anyway, is you have an electron beam which impinges on a just heavy metal like tantalum. And then after that, you can have the tantalum make its own neutrons, or if you want to enhance this process, you can put beryllium, which has very loosely, beryllium nucleus basically just very loosely bound alpha particles with a neutron in between. And if you hit it just with anything, it will breaks up and emits a neutron. The neutrons that come out are fast neutrons, epithermal neutrons. So what you do is you put a piece of plastic, and this, if you're lucky, one of the neutrons hits the plastic, slows down, and comes out at there's a whole wide energy range, including epithermal neutrons, which is what we care about. Okay. So the overall facility, this is like a schematic, looks sort of like this. You have got your electron beam, you have this you get neutron beam coming out, you have your object, which we have an encrypting filter, which essentially is, again, tungsten and molybdenum of an unknown amounts. Notionally, the hosts would provide that, okay? And you will not know what it's made out of. Well, you'll know what elements it's made out of, but not the that is made out of, okay? And what happens, eventual neutrons are detected by your lithium, in this case was lithium-6 glass scintillator. You get the pulse signal, you get the neutron detection signal, you calculate the time difference, that gives you time of flight, from where you do mv squared by 2, that gives you energy, okay? So, we we started by doing some basic measurements, we put in some amount of tungsten plates. So we first measure the distribution of the open beam. Ignore the steps. This is simply rebinning. We like change the bin size as we're moving out, so we got this sync effect. But it's more interesting if we just take the ratio of the open beam to the measurement where we had tungsten plates. And you can essentially see tungsten absorption due to tungsten resonances at a very specific and expected energies. The dotted lines here are the resonances, and they're absent because there was no molybdenum here, but there was quite a bit of tungsten. So then we did another measurement where we added molybdenum, and you start seeing molybdenum resonances. Eventually we had only molybdenum. You can see clearly one resonance here, one resonance here, one here. And this is all the way to 200 eV. Originally we were planning to do measurement where we're going to use just this part of the spectrum from 1 to 220 eV. Turns out that we had very good energy resolution up to 200 eV. That was great. Great surprise. Most of the time, when it comes to experiments, surprises are bad ones, but this was a very pleasant surprise. Okay, so how we're going to do this experiment? Well, we have our molybdenum tungsten mix. First of all, what we'll do is can we see isotopic hoaxes? So we separate hoaxes into two categories. Isotopic hoaxes, where someone shifts the isotopics. Remember, weapons grade versus reactor grade plutonium, something like that. And another one, when you change the geometry. And in this particular case, what we do is that we'll replace the cylinder with basically a cube box, if you will, such that along the z-axis, the thickness is exactly the same. Remember, this is simply zero-dimensional measurement, okay? So if you were just do measurement along this line, you would not be able to tell the difference between this and this. But that's okay. What we do is, first of all, we compare these two things with each other. Okay, so that gives us certainty that there is no isotopic hoaxing going on. Then what we do is we do rotations, random rotations. In this case, we simply chose 45, 90 degrees, just because we have to pick an angle. In real life, it would be truly random. Okay, and now you do measurements under this, and now do comparison under this. Okay, and at this point, geometry starts playing a role in the transmission. At this point, you're able to tell the difference. Okay. Okay, so this is very roughly, I don't know if I can tell here, but this is basically our setup. We had a little box over here with the molybdenum tungsten sample, and then here we had our encrypting foil, which was made out of molybdenum and tungsten. Okay. All right, so first measurements we did, we shifted the isotopics. We took the same cylinder, we keep filters the same, okay, of course. Compare a 90-10 ratio molybdenum tungsten to 50-50 hoax, where it's half the thickness is molybdenum, half of tungsten. And you can even just by eye, right, you can tell the difference. What happens that because you increase the amount of tungsten, okay, the tungsten resonances become a lot broader and a lot deeper. Okay. At the same time, the molybdenum resonance, which was fairly small, now has almost disappeared. And when you go all the way to 1090, where there's barely any molybdenum left, the molybdenum resonance is basically gone. And same thing happens with the other resonances, where the tungsten resonances have become bigger and thicker. You can run a very simple chi-square test and ask yourself, what's the probability that these two things are identical? And it will tell you it's exactly 0%. Let's see. Oh, yeah. The fairly, like, this is your chi-square, this is number of degrees of freedom. I mean, there's no way these are the same. Okay, that's simple. Now, we do the geometric hoaxes. Replace a cylinder with a box, or parallelepiped, to be specific, such that along z-axis they're identical. Okay, same thicknesses. You do your measurement, and you do your chi-square test, and look, 65% passed. Okay, of course it passed. Like, we made it to be that way. We made the geometric hoax such that along one direction it will pass through the check. Then what you do is that, okay, now to see whether this is an geometric hoax, okay, we do rotations. We rotate it by 45 degrees, so 65 degrees. And these are the measurements under 45 degrees and 90 degrees. And while in this slide the differences were obvious, they were enormous, here the differences are tiny. I mean, you really have to squint and look hard to see that there is some difference. However, when you run your chi-square test, the chi-square test is this. Okay. So chi-square will tell you, yes, the difference is small. This is chi-square, this is the number of degrees of freedom. But the probability that they are the same is exactly 0%. Okay. Now you'll tell me, okay, but how do you know that this is your system really works? You know, what if it's your accelerator's energy change or your detector's gain change or something else happened? How do you know that this signal is truly due to the changes in geometry and isotopics? Okay, so we take the same object and we do multiple measurements at different times. Okay, 3 hours later, 4 hours later. Can we confirm that these new measurements of an honest object matches the original measurement? Okay, so basically you want, every time you have a detection system, you have to make sure that you have to check your type 1 error, you have to check your type 2 error. Okay, so in this case, this shows us that our type 2 error is very small. Now we have to make sure that our type 1 error, okay, false positive rate is also very small, right? After all, the system could be unstable. It could be putting honest objects, but because the beam has shifted, it's going to tell you that no, they're not the same. So these are the results of the, okay. There we go. These are the results of the honest candidate comparisons under 0 degrees, 45 degrees, and 90 degrees. And essentially, you end up having a match throughout every single one of them. And by the way, these measurements, when we did this thing, like, it was done after the beam tripped, after they had to go inside, they had to do access, they had to change a number of things, and we still managed to get exactly the same spectra for the honest objects. General summary of what was done. The first thing we did is that we compared our isotopic hoaxes to the genuine, and we can do chi-square test, get a p-value, and that's an obvious reject. Then we do a geometric hoax check, okay, and we find out that yes, under the 0 degrees, there's a match, but under other angles, you end up having disagreement, so that's a reject as well. And for the honest candidate, we have agreements under every single angle that was measured, 0, 45 degrees, and 90 degrees. Okay, so this is interesting, but next thing, a question we ask ourselves, I sort of want to ask yourself, okay, but in a realistic scenario, so this principle works, we show it in the experiment that it works, but let's think about practical considerations, okay? We're not going to build these huge facilities for just doing a warhead verification facilities, but there are a few of them, and it's going to be very difficult to bring weapons to RPI and do measurements, or even Los Alamos. So just to understand what we're talking about, this is the size of the RPI Gaitner laboratory. It's about 336 meters. And this is a Los Alamos, this is Google Maps pictures, Los Alamos proton accelerator, spallation source. That's about 1 kilometer big, okay? So the scales are little geological scale instruments, okay? This is what we call, we call this Mesoscale Physics, okay? Different from Mesoscale. Question is, can we do the okay, you don't need these huge facilities to make neutrons. Okay, these facilities are so. The problems, they were not built for warhead verification. They were built for doing high precision cross-section measurements. We don't need that precision, and we don't need intensity. Can we come up with something that is much smaller? Okay, so for example, can we do it with a simple DT source? Can we take a DT source, build a collimator, shield it, put the detector 5 meters out. Our energy resolution is not going to be as great as what I showed before, but maybe that's okay. Maybe we don't need such high resolutions. So we have been doing some simulations to see if that is feasible. So I have a student who's writing his master's on this, and actually has already written it. And the question is, can we do this with like DT generators, or better yet, with Linux? DT generators, because we happen to have. But what you want to optimize is epithermal neutron efficiency, how many epithermal neutrons you make. You want to, understand what happens to your time of flight reconstruction and what time smearing it's causing. And you need to be able to shield this thing, because what happens is that lots of neutrons, they are not going to go from your source, thermalize, and go straight to your beautiful detector. They're going to bounce around the room, come with completely different time of flight values that will give you completely wrong energy reconstructions, and you need to be able to suppress that. When it comes to 14 MeV neutrons, it's notoriously difficult to do that. We're done, essentially. So the hope is to go from mesoscale to table scale, okay? Those who know Spanish know that mesa means a table. All right, so the simulation that we're done, essentially, is this. We built this, the idea is that we're going to build this large spherical shielding, okay, of borated polyethylene and boron, with a neutron source over here and a moderator over here. And we'll put our detector over here, and we surround it with boron as well. You really have to do this. And after some simulation, it turns out that it has to be fairly large. It has to be about 1.8 meters tall sphere that will weigh a couple of tons. Still, a couple of tons is much better than kilometer-long facility. And then we ask ourselves, okay, what resolutions will we get? Will we be able to observe those absorption lines? So we did simulations in Giant, for moderation, and first thing we looked is the moderation time, okay? And so we're trying to optimize the moderator thickness, and they essentially found that the moderation time is independent of moderation thickness, which sort of kind of made sense. But essentially moderation time, depending how you look at it, is something like, results in like a half microsecond smear on your time of flight reconstruction. So if you go out to 5 meters, that already end up being extremely small. We looked at the efficiency of. And okay, can we actually reconstruct stuff or not? And this is one of our better results, which includes room return. This is including shielding, including a concrete room, neutrons bouncing from stuff, coming back to our detector, capturing on lithium-6. And in this particular case, we had a mixed target where we had a tungsten and silver. Silver has this very nice strong line over here. And the blue is the actual energy of the neutrons when they hit your detector. And the red is the time of flight reconstruction. Okay, and essentially you get fairly good resolution, except that you are not hitting. This thing should be blacked out, but they are not, because there's enough neutrons scattering around. There's a couple of other simulations where we're comparing different thicknesses. Eventually, like the student Ezra looked around and finally found out that what's happening is that lots of neutrons are scattering from inside this shielding around the detector. Okay, so they lose energy in the process slightly, and that causes them to come from this energy to this energy, and ends up filling these very narrow lines. Okay, so instead he tried this other geometry, this polycone, which basically has kind of like scales, so that the detector cannot see the scattering surface. Okay, and that's a dramatic improvement right away. So like all this, what I said ought to have been blacked out, now they truly go to zero. Okay, and here the only reason the red doesn't come to zero is because of the moderator smearing. Okay, all right, I'm going to finish up because we're running out of time rapidly. So what we have done some experimental feasibility work with nuclear resonant fluorescence. We have done Monte Carlo simulations for epithermal neutrons, and we have followed it up with experimental work, which has confirmed that you can do these things. By the way, those measurements I showed at RPI, each one of them took 5 minutes. Okay, so a pair of comparison would take like 10 minutes. Other applications, you could use this thing for archaeology. Maybe, let's see, you can use this for archaeology. You can use this for stockpile stewardship. And the question is, can we make these epithermal techniques, which have been developed a long time ago, but have never really been used because it involves such large facilities and access to them and stuff like that. Can we pull this off using small, compact, possibly mobile platforms, and thus make this technique more ubiquitous? To deal with, of course, we need to work with national labs because they are going to do verification, not us. And of course, we need to talk to Russia about these things. To do verification, you need 2 countries, not one. This takes basically catalysts for future arms control treaties that go actually after the weapons themselves and not just delivery vehicles. Okay. Hopefully this will help overcome the technological barrier, you know, that needs to be done in order for these treaties to become reality. But in general, I want to finish by saying that, you know, what I'm trying to think about this as a scientist, as a physicist. What can I use? Okay, what can I do to help solve big societal problems? Okay, nuclear weapons being probably the largest one of them, right? And I'm going to leave you with just a picture of the students that are in my group that are making this work, that contributed. Just defended 2 days ago, and he did lots of the NRF work. And with that, I'm ready for your questions. Yes.
The values you gave for the gold standard particle, how reproducible, what kind of variation do you get in those, or would you expect empirically?
So I don't have an answer off the top of my head. I think the variation will be fairly small because it's a huge statistical set. Both spectra are extremely data rich. We only did just a few measurements, and essentially in all cases there were like we got essentially very similar values. Yeah. Yes.
How would your adversary trust that your system does what you say it does? Instead of having a single pixel, you could have.
Can do is, the question is, what I should describe is what is accessible to who. The weapon is only accessible to the weapon, and the encrypting foil are accessible to the host alone, but the inspection party has visual access to them. They know that, for example, they are not swapping the encrypting foil or something like that between measurements, right? As far as the detector is concerned, everyone has access to it. In principle, they can open a simple scintillator with a simple PMT. Okay, those are simple devices, simple analog devices that are kind of can be checked. In fact, you can put 2 detectors. You can put their detector and our detector. Okay, and they ought to give the same signal, right? Yes. Yes. All right, it's a 3 All right, like, you drew faster. So.
So you're planning to do this at Nevada test site, right?
That's right. Yeah.
Have you decided what you're going to use as your encryption foil for this?
So for that measurement, I don't think we would simply do just simple bare measurements without using the encrypting foil. The idea being is that, you know, if this thing can work with a simple bare object, then the effect of encryption foil is fairly simple to add. Yeah, that would be the ideal, what you're saying. But I don't think if I ask them for plutonium plates, that will be probably too complicated. Yeah, no. Yeah. Let's see. What wants a student to ask this?
So for the rotations, how would you ensure that the rotations are actually truly random and not just like designed in such a way that they control which
That's right.
rotations they add so they match just the.
That's right. Right. So in principle, if the rotations were not, it's a very good question. They could design an object which would actually be different but identical under specific rotations, right? So it truly has to be random. So the inspectors can choose the angles. They can flip a coin, right? Inspectors are the ones who are interested in this cheating not to happen, right? Or you can have something that detects just random number generator and tells you the angle or something like that. Yeah. Yeah.
So you needed shielding. What was the dose rates with and without the shielding that you were looking at?
For the RPI measurement, well, I don't know what rates were in the actual moderator room. In the room where the detector was, it was something like millirem per hour. I was actually sitting right outside, and they didn't even bother blocking me from going inside, which I did not. This in a real treaty verification?
Have you tried other applications?
Other applications. We have primarily focused on treaty verification. We think that this could also be used for other applications like archaeology. Like a simple example. In Belgium, if I'm not mistaken. So the idea would be to, instead of having so once you go into archaeology or once you go to actual other types of non-proliferation treaties, for example, vis-a-vis Korea, where maybe you don't need encryption in that case, right? So then there's many other things you can do. For example, you can build pixelated time-of-flight detectors. Los Alamos they use this they have this multi-channel microchannel plate detectors borated with boron. So the boron captures neutron, makes an alpha. You end up getting 50 micron resolution. It's beautiful. And when I found out, I was like, "Ooh, I'd like to buy one for our lab." And found out it's $200,000. Again, because the purpose was to do this extremely high precision measurements. You could, in principle, envision systems where you could have, for example, silicon photomultiplier arrays, right, which cost a few $1,000s with either lithium glass on it, or with simply lithium directly on it to ionize the cells directly, or a number of other scintillators, LICAF and things like that, where you could achieve like millimeter resolutions, but have something that's truly compact, does not vacuum pump, is not very expensive. Yeah. Okay.
Okay, let's
Maybe there's one. We'll talk later. Thank you. Yeah.